Good afternoon, ladies and gentlemen. My name is Hu Jie from South China University of Technology. The topic of my presentation is using lightweight functional aggregates to mitigate the acidification damage in external anode mortar during cathodic protection. I will introduce our work in the following 5 parts. First, I would like to briefly introduce the background of this study. When we talk about the durability of reinforced concrete, corrosion damage of the reinforcement is always an important issue because the accumulation of corrosion products will cause cracking, reducing the surface life of reinforced concrete. Further, the maintenance and repair related to corrosion of the reinforcement also cause significant economic loss. In order to solve the problem, different methods and techniques can be used. Among them, electrochemical techniques are proved to be an effective corrosion mitigation and repair techniques for reinforced concrete. Cathodic protection is a very important electrochemical technique and especially suitable for corrosion protection of reinforced concrete under chloride-contaminated environment. Cathodic protection is to use external power to negatively polarize the embedded reinforcement, thus thermodynamically inhibiting the anodic reactions related to corrosion damage. However, this technique also has some disadvantages. During cathodic protection, the anodic reactions will occur mainly on the surface of the primary anode, consuming hydroxide ions in the vicinity of the primary anode and leading to a pH drop of mortar solution. This is defined as acidification damage in external anode mortar, which will result in dissolution of hydration products, porous microstructure, and reduced adhesion strength. Further, the conductivity of the external mortar is poor. The acidification will further cause non-uniform distribution of the conductivity, leading to over or under protection and reduced protection efficiency. Therefore, improving the acidification resistance of the external anode mortar is of great importance. The optimization of the external anode mortar was mainly focused on improving either its conductivity or mechanical properties in the reported studies. Different conductive enhancing components were used to improve the conductivity of the external anode mortar. Among them, carbon fibers were the most reported and applied one due to their superior conductivity. Geopolymer-based external anode mortar was also proposed to increase its mechanical property. However, to our best knowledge, the improvement related to the acidification resistance of the external anode mortar was not reported. In our previous study, another type of lightweight functional aggregates loaded with modified agar gel was prepared with very low resistivity. Therefore, it significantly increased the conductivity of the mortar when they replaced the normal used insulating aggregates and combined with carbon fibers. Further, the functional aggregates also improved the uniform conductivity distribution of the mortar. Therefore, the above prepared lightweight functional aggregates can be potentially used to prepare the high-performance external anode mortar for cathodic protection. To this end, the objective of this present study is to investigate the retarding effect of the lightweight functional aggregates on acidification damage both for the primary anode and the secondary anode mortar. This slide summarizes the raw materials used in this study. The volume fraction of fine aggregates was in the range of 20 to 14 volume percent, and the volume fraction of carbon fibers was fixed at 0.75 volume percent. After curing for 28 days, the mortar specimen together with the reinforcement was immersed in simulated concrete pore solution. For accelerating the acidification damage, 200 microampere per square meters was applied to the mortar specimen. The electrochemical measurements were used to characterize the influence of functional aggregates on the electrochemical behavior of the primary anode. Besides, the morphology and composition alterations of the primary anode and the mortar matrix were evaluated by OFM and SEM observations combined with the DEX analysis. First, let's look at the influence of the functional aggregates on the primary anode. When ordinary aggregates were used, the potential of the primary anode increased with time, and the specimen with higher aggregate content presented higher anode potential. For specimen LFA, the anode potential also gradually increased. However, it presented significantly lower anode potential compared to the reference specimen. The lower anode potential of specimen LFA indicated that functional aggregates maintained the high catalytic activity of the primary anode during the acidification damage. It was also observed in PD curves that the anodic current density for specimen LFA was higher than the reference specimen, confirming that the functional aggregates were beneficial for maintaining the high catalytic activity and stability of the primary anode. This slide shows the impedance of the primary anode. During the initial stage, impedance for all specimens were very small, indicating the good catalytic activity of the primary anode. After the acidification damage, the catalytic activity of the primary anode was reduced, evidenced by the significantly increased impedance for all specimens. However, compared to specimen NA, the impedance for specimen LFA was slightly lower. The impedance of the primary anode was fitted by random circuit, and this slide shows the derived mortar resistance and charge transfer resistance. Before the acidification damage, the mortar resistance and the charge transfer resistance for all specimens were at the similar low level. After accelerated acidification damage, the mortar resistance and the charge transfer resistance for the reference specimen was significantly increased. When the lightweight functional aggregate was used, the mortar resistance and charge transfer resistance was also increased. However, specimen LFA presented lower mortar resistance and charge transfer resistance compared to the reference specimens, indicating a better catalytic activity of specimen LFA after the acidification damage. This slide shows the same image of the primary anode surface after the acidification damage. The spalling of sintering MMO coating was observed, which was resulted from the acidification damage of the primary anode. However, compared to the reference specimen, the acidification damage degree for specimen LFA was less severe. Further, hydration products were observed on the primary anode surface, indicating a more compact macrostructure and higher adhesion strength at the primary anode secondary mortar interface. Besides the primary anode, the functional aggregates also significantly influence the acidification damage process in the secondary anode mortar. Based on OFM image, the acidification damage of the secondary mortar could be divided into two regions. The first region was the severe acidification damage region, within a distance of about 300 micrometers from the primary anode surface, exhibiting porous macrostructure and a very bright color. In this region, no obvious effect of the functional aggregate was observed based on the OFM images. Beyond the distance of about 300 micrometers, the acidification damage mainly occurred around the ITZ and resulted in cracks in the mortar matrix. In this region, the functional aggregates halted the further propagation of the acidification damage, evidenced by the denser microstructure in ITZ and less cracks in the mortar matrix. This slide shows SAM images in the vicinity of the primary anode after acidification damage. It confirmed that compared to specimen NA, specimen LFA presented a denser microstructure in the severe acidification damage region. Further, the cracks in the mortar matrix were also significantly less for specimen LFA. In ITZ region, it was observed in OFM images that very bright color was observed for the reference specimen, indicating severe acidification damage and subsequently more porous macrostructure in this region. In comparison, the acidification damage in ITZ was dramatically mitigated by the functional aggregates, evidenced by the less bright color in this region and the smaller influenced area for specimen LFA. Based on SEM images and the related index analysis, specimen LFA presented a denser ITZ compared to specimen NA. Further, the calcium silica ratio in ITZ was significantly higher for specimen LFA. Generally, the porosity of the mortar matrix was reduced with the distance from the primary anode, both for the specimen NA and LFA. It was observed that the mortar matrix presented similar high porosity for both specimens in the region within a distance of 150 micrometers from the primary anode surface, indicating severe acidification damage and subsequently porous microstructure in this region. In the region with a distance beyond 150 micrometers, the porosity of specimen LFA was lower compared to the reference specimen, indicating that the functional aggregates halted the propagation of the acidification damage in this region. Further, the higher calcium silica ratio of specimen LFA indicated that the lightweight functional aggregates mitigated the dissolution of hydration products and calcium leaching in the external anode mortar. Based on the above experimental results, the influence of the lightweight functional aggregates on the acidification damage in the external anode mortar is summarized as follows. Due to the release of hydroxide ions from the functional aggregates, LFA maintained the high alkalinity of mortar pore solution at the interface. Therefore, the dissolution of hydration products was halted by LFA. As a result, the porosity of the mortar matrix for specimen LFA was significantly lower compared to specimen NA. And the specimen LFA presented a denser microstructure and adhesion strength at the interface. The denser microstructure at interface might help the diffusion of hydroxide, which further mitigated the acidification damage in the secondary mortar. For the primary anode, the ability of LFA on maintaining the high alkalinity in mortar matrix will also maintain the high catalytic activity and the stability of the primary anode. This slide shows the main conclusions of this study. Due to the time limitation, I will not repeat it. Besides the results I present today, we also applied the high-performance external anode mortar based on the lightweight functional aggregates prepared in this study for corrosion protection of reinforced concrete specimen, and we do have some positive results. And I hope I will have the opportunity in the future to introduce our further results. At last, I would like to thank my PhD student Guo Wenhao, who mainly conducted this research work. He has already graduated and now works in Foshan University. I also want to show my gratitude to all the colleagues and students in our research groups and the financial support related to this study. That's all my presentation. Thanks for your attention.